neutron diffraction analysis. This is the first use of neutron diffraction analysis, that is locating light atoms. In between the heavy atom, the light atoms can be detected by the use of neutron diffraction. The fact that neutron scattering factors are similar for all elements, uh, they are not exactly similar, they are nearly similar. For example, here is the neutron diffraction pattern for carbon, nitrogen, chlorine, uh, mercury. These are very close to each other. So that is why it is said that neutron scattering factors are similar for all elements, means that light atoms scatter neutrons as effectively as heavy atoms. So both light atoms and heavy atoms, they will effectively scatter the neutrons, and that is why the light atoms can also be detected and heavy atoms can also be detected. Therefore, the light atoms can be located in the crystal structure. For example, extra scattering factor for deuterium and tungsten. There is a large difference between the atomic masses of deuterium and tungsten. Tungsten is a heavy atom, deuterium is a very light atom. So, in case of extra scattering, the extra scattering is very small in case of deuterium and it is high in case of tungsten. But when we see the neutron diffraction of deuterium and tungsten, they are nearly equal, the 0.667 and 0.486 respectively. These are the scattering factor for deuterium and tungsten, they are nearly equal. So it's mean that neutrons are diffracted effectively by heavy atoms and light atoms, and we can detect the light atoms by means of by studying this graph of neutron diffraction. The property is particularly useful for locating hydrogen atom. The property of the neutrons, that neutrons are diffracted from heavy atom and light atom. From both neutrons are diffracted very well. So this property of neutron is very useful for locating hydrogen atom, which is a light atom in any material structure, and the location of locating hydrogen sometimes be difficult to do in X-ray determination, because X-rays, in case of X-rays, they will not detect light atoms, because X-rays are not scattered from, they are very less scattered from light atoms. The extra scattering factor will be very small in case of light atoms, so light atoms will not be visible in the X-ray diffraction pattern, especially if the hydrogen atom are in the presence of heavy metal atom. So there is heavy metal atom and there is hydrogen. So in the presence of heavy metal atom, we cannot locate hydrogen. It's X-ray diffraction. In the X-ray diffraction pattern, hydrogen peak will not appear, because X-rays are not much scattered from hydrogen. Accordingly, many neutron studies in the literature have been done with express purpose of locating hydrogen atom. So, in many studies, neutron diffraction is used for locating the hydrogen atoms in the structure. Or of exploring hydrogen bonding with the help of neutron diffraction, we can also study the hydrogen bonding in material structure. Here is another application that neutron diffraction analysis can be used for heavy atom as well, or light atom, and for heavy atom for both neutron diffraction can be used. The crystal do not absorb neutrons, so they are also useful for studying systems containing heavy atom that absorb X-rays very strongly. Some heavy atom will not scatter X-rays, so that heavy atom will not be cannot be studied by X-ray diffraction analysis. So they will be studied by neutron diffraction analysis, because neutrons are not absorbed by the crystals. So they are useful for studying system containing heavy atom, and heavy atoms, in case of heavy atom, they will absorb X-rays very strongly, and X-rays will be very little scattered from the heavy atom. Here is another application, and that is similar atomic number and isotopes. With the help of neutron diffraction analysis, uh, we can detect the isotopes. Isotopes are those elements which have same atomic number but atomic mass is different. So isotopes can be differentiated with neutron diffraction analysis. Atoms near each other, in the periodic table have a very similar X-ray scattering factor, which are very close in the periodic table. They will show very close X-ray scattering factor, and cannot always be distinguished in an X-ray structure determination. So they have, because their peaks will overlap because they have X-ray scattering factor. So they cannot be studied through X-ray diffraction analysis. Oxygen and fluorine, they are close to each other in the periodic table. This is the example. Or similar metal in an alloy is the example. So oxygen and fluorine, they will not be differentiated in X-ray diffraction analysis pattern. A neutron structure determination may be able to identify atom with similar atomic number. So neutron diffraction analysis can be used for such type. For example, for case of oxygen and fluorine, they are very close to each other. So their stress scattering factor is very close to each other. In the X-ray and X-ray diffraction pattern, the peaks will overlap, but neutron diffraction analysis, they can be differentiated from each other. And neutron structure determination is also helpful in identification of the atoms which have similar atomic number but different atomic mass. That is, by neutron diffraction analysis, we can differentiate between the isotopes of an element. We can explain the magnetic properties of the material. We can study the magnetic properties of the material by neutron diffraction analysis, as well as scattering of neutron by the nuclei. We have already studied that the neutrons are scattered by the nuclei of atom. But there is additional scattering, that is magnetic scattering in case of paramagnetic material. So when neutrons strike to the nucleus, they will be scattered by the nuclei, and they will also be scattered due to paramagnetic behavior of the atoms. So there will be additional scattering of the electron, which is called magnetic scattering. This magnetic scattering is due to spinning of neutron. Neutron which strike with the nucleus of the atom, the neutron has spin, and this neutron, when it is spinning, it possesses a magnetic moment. So magnetic moment of this neutron will interact with the magnetic moment of the paramagnetic moment, and due to this interaction of the two magnetic moments, magnetic scattering of neutron takes place. The atomic magnetic moment is due to the alignment of the electron spin. This is the reason how magnetic moment in an atom is produced. Magnetic moment in an atom is produced due to alignment of electron spin. When two electrons are unpaired, their spins will be parallel, or two or more than two electrons are unpaired, their spins will be parallel, and the material will be paramagnetic. And so this interaction, this is about this type of interaction, that is neutron magnetic moment attract with the magnetic moment of the paramagnetic atom. This interaction of two magnetic moments will decrease with increasing Bragg angle. When the Bragg angle is increased, the interaction of neutron magnetic moment with the paramagnetic atom's magnetic moment will decrease due to size of electron cloud. Magnetic scattering of polarized beam of neutrons. Polarized beam of neutrons means actually neutrons are spinning particles. The spin may be clockwise and anti-clockwise. When for example, when there are more number of neutrons in clockwise spin state as compared to the anti-clockwise spin state, then this beam of neutron is called polarized beam of neutron. So polarized beam of neutron is that beam of neutron in which one of the spin state is highly populated as compared to the other spin state. Highly populated spin state may be anti-clockwise or it may be clockwise spin. Any of the spin state may be highly populated, and that type of neutron will be called polarized beam of neutron. So magnetic scattering of this polarized beam of neutron from these ordered magnetic moments, that is the magnetic scattering will take place, we have already studied, due to uh, interaction of the magnetic moment of neutron with the ordered magnetic moment of the atoms. It will give rise due to this interaction, magnetic scattering of the neutron will take place, and this new magnetic scattering of the neutrons will give rise to an additional peak in the neutron diffraction pattern, and this additional peak will be called uh, magnetic break peak. There can be one peak and there can be more than one peaks. For instance, the structure of nickel oxide as determined by X-ray diffraction is the same as sodium chloride. But when we take the neutron diffraction of nickel oxide, its structure will be different from sodium chloride. In neutron study, however, below 120 Kelvin, below these structures, extra peaks appear. And these extra peaks are magnetic break peaks. These extra peaks are due to magnetic scattering of the neutron. This extra peak due to magnetic interaction or magnetic scattering of neutron, and when we calculate the cell dimension from these peaks, this gave a magnetic unit cell which has a cell length twice that of the standard cell. That is for example, in X-ray, the nickel oxide structure is similar to sodium chloride. So when we study below 120 Kelvin and in neutron study, the cell dimension which are obtained, it will be twice as compared to the cell of the sodium chloride. This arises because of alternate close-packed layer of nickel atom have their magnetic moment aligned in opposite direction, giving rise to antiferromagnetic behavior. Nickel atom show below this temperature, that is 120 Kelvin, nickel atom show antiferromagnetic behavior, and antiferromagnetic behavior is due to the reason that in the layers the electrons are having spin in opposite direction. That is, total spin that are clockwise are equal to the total number of spins that are anti-clockwise. So the material is antiferromagnetic, and a neutron magnetic moment will interact with these antiferromagnetic atoms, and magnetic interaction will take place and extra peaks will appear. Here is a structure, the magnetic ordering in nickel oxide. The nickel planes only are pictured. Here the shaded area, these show the nickel planes, and here is in these circles are electron spins having opposite magnetic moments. So some spins, this is clockwise, this is anti-clockwise. Note that the magnetic unit cell length is double that of the normal unit cell. So when we calculate by these peaks that are obtained due to magnetic interaction, the unit cell dimension which are obtained are called magnetic unit cell dimension or magnetic unit cell. So from the normal unit cell, the magnetic unit cell dimension will be double.